Right, let's talk about how to solve 99% of pressure questions. Right, so I'm Ting from the A1 Physics, where I specialize in Sec 3 and 4 O-level pure physics tuition. And let's get right into it. Right, we're going to be going through manometer, barometer, how they work, as well as some worked examples. Now, over here, we have this thing called a manometer, and essentially the idea of manometer questions is very simple. Right, there are 3 steps to solve any manometer question. Right, step 1 is to draw a line on the lower water level. So we can see over here, there are 2 different water levels. This one is the higher water level, and this one is the lower water level. Right, so step 1 is to just draw a horizontal line on the lower water level, just like this. Right, step 2 is to draw the pressures on both sides of the line, and now I'm going to go into a bit more detail on the concepts over here. Now on the left side, we have atmospheric pressure, and essentially what is atmospheric pressure is you can just think about it as the Earth pulling down the atmosphere, right? So atmospheric pressure is the Earth pulling down the atmosphere, and that's why atmospheric pressure is acting downwards, right? The Earth is trying to pull down the air over here. And as we can see, on the left side, this part of the manometer is exposed to the air. So that's why there's atmospheric pressure on the left side, right? Whereas the right side, this one is inside a sealed container, so there is no atmospheric pressure on the right side. Now over here on the left side, we also have water pressure, and essentially what is water pressure is the Earth pulling down the water, right? So for this section of the water, the Earth is trying to drag down this section of the water, and that's why there is water pressure acting over here, right? The Earth is trying to pull down the water. So same thing as atmospheric pressure, water pressure also acts downwards, and we can calculate water pressure using rho GH, where rho refers to the density of water, G is the gravitational field strength, which is usually 10, and height is the height of the water column, right, which is over here. Our height is this height h over here, right? And on the right side, we have gas pressure, where the gas is trying to push down against the water over here, right? So now that we've drawn the pressures on both sides, we just want to make an equation, right? And the idea is that the left side pressures equals to the right side pressures. So over here, we have atmosphere plus rho GH equals to gas. Right, this one is our pressure equation for this question. Now, in case you're wondering why is the left side pressures equal to the right side pressures, you can think about it like this, right? If the left side pressures was even bigger than the right side, then it would push the water down over here, right? And if the right side pressures was even bigger than the left side, then it would push the water down even further. So because the water is now in equilibrium on this line, we can say that the left side is equal to the right side pressures. Right, just take note, this equation is not always true. It depends on the scenario. Right, so for example, over here, if the water pressure on the right side is even higher and we draw our line on the lower water level, our equation becomes atmosphere equals to rho GH plus gas. Right, this one is our equation for this specific manometer. So don't go and memorize the equation. The equation can change depending on the manometer. But the idea is that the pressures on both sides of the line are always equal to each other. That one is always true. Right, so let's do some practice over here. Just feel free to pause the video and try this question for yourself. Right, so over here, the idea is that we draw a line on the lower water level and we draw the pressures on both sides. Right, so on the left side, there will be atmospheric pressure, and on the right side, there will be water pressure, rho GH, plus gas pressure. So our equation becomes atmosphere equals to rho GH plus gas, and we know that the atmospheric pressure is this one, and we can calculate rho GH, right? So our equation becomes 1.0 times 10 to the power 5 equals to 1000 times G, which is 10, right? Gravitational field strength is usually 10, and the H over here will be 1.9 meters. Must always convert to SI units first, plus gas. Right, and solving this equation, we can find the gas pressure. Right, so gas pressure equals to 81,000 pascals. Right, quite straightforward. Now, for the second one, the water in the equipment is fully replaced with mercury and it connects to the same flask. Right, so what happens to the distance between the mercury levels from P to Q? Right, so what you gotta understand is that when you change water into mercury, what's gonna happen is that on the left side, if we were to draw the line over here, on the left side, there's still atmospheric pressure, right? On the right side, there is still gas pressure, and on the right side, there is the pressure of the mercury. Right now, it's the rho GH of the mercury. Right, and the thing is, the atmospheric pressure didn't change. The gas pressure didn't change, right? So our equation is still atmosphere equals to rho GH plus gas, right? It's the same equation, it's just that over here is the rho GH of water and over here is the rho GH of mercury. So in other words, the water pressure last time is equal to the new mercury pressure, and your job is to find the height of the mercury. Right, so atmosphere equals to rho GH plus gas, and for atmospheric pressure we know is 1.0 times 10 to the power 5. For rho GH, now we're using the rho GH of mercury, so it will be 13600 times 10 times the height of the mercury plus the gas pressure, which we know is 8100. Right, and solving this equation over here, we can find height h over here. So h equals to 0.14 meters. Right, so answer for this question is 0.14 meters. The height of the mercury over here is 0.14 meters. Right, so with a barometer over here is really the same idea as a manometer. Right, so step 1 is we want to draw a line on the lower water level like this. Then we want to mark out the pressures on both sides. So on the outside of the barometer, there is the atmospheric pressure outside. Right, this atmospheric pressure is trying to push down on the water over here. And on the inside of the barometer, assuming that this barometer is made out of mercury, there will be the pressure of the mercury. Right, pressure of mercury equals to rho GH. Now over here it depends on whether inside is vacuum or trapped gas. If inside is a vacuum, means that there is no air inside, then the equation will be rho GH equals to atmosphere. Right, we equate the pressures on both sides together. Now if inside was not vacuum, if inside was trapped air, then now this trapped air is going to try to push down onto the water. Right, so it's going to exert this air pressure called the trapped air pressure. So now our equation becomes air plus rho GH, right, which is the inside, equals to the outside pressures. So equals to atmospheric pressure. Right, and that's how you make your barometer equation. So let's try with some questions. Right, so if you want, feel free to pause this video and give this question a try. And if not, let's go through this question together. Right, so over here, same thing, we want to draw our line on the lower water level like this. And let's look at the barometer P first. Right, over here for barometer P, we can see that on the outside, we have atmospheric pressure. On the inside, we have mercury pressure. And over here, we have trapped gas of pressure 16800 pascals. Right, this one is the pressure of the trapped air on top. So now our equation becomes atmosphere equals to 16800 plus rho GH. Right, and very easily we can solve this equation to find the atmospheric pressure. It's just 16800 plus rho, which is 13600. Right, that's the density of the mercury, times 10 times the height. So the height over here is 0.7 meters. Remember, must always convert to SI units. Right, and answer for this is 112,000 pascals. So that's the atmospheric pressure. Right, so how do we find the pressure of the space above the mercury in tube Q? Right, so we're trying to find this pressure of the trapped air on top of Q. Right, so how do we find this pressure? We just make our barometer equation. Inside there'll be trapped air, and there'll also be the mercury pressure rho GH. Right, and on the outside, there'll be atmospheric pressure. So now our equation becomes air plus rho GH equals to atmospheric pressure. Right, so rearranging this equation, we will get air equals to atmosphere minus rho GH. So atmosphere we know is 112,000, rho GH we know is 13600 times G times H, which is 0.55 meters. And answer for this question is 37200 pascals. Right, so for manometer and barometer questions, it's just about drawing the line and writing down the pressures on both sides and making your equation to equals the pressure on both sides. Right, so I hope you found this video helpful. Go ahead and look at the other videos on this channel for A1 physics tips. And if you need O-level physics tuition, just go to my website, the a1physics.com. Alright, I'll see you soon.